hopefully with the Edsby crew, so that way all the class can watch. And those of you watching on TV, although I notice I have no people viewing currently live right now, but just orientation is locked. So orientation is locked. I don't know how to unlock orientation. We'll see. Can I unlock orientation? No, I can't. I guess orientation is locked. Let's see how that works out. And just sharing the link, sorry for that. Mr. Gregorius Math. Live. Hey, it looks like I've got this. I'm going to share. Copy. And paste. Great. I don't know how much of the board I'm going to be able to see from this, but let's try and aim for... That's not going to be enough. From that line over. Okay, perfect. Maybe I should have got this ready before going live, but whatever. That's the way it goes.
Do it on the fly.
Yeah, why not? Okay, so today we are talking about the dot product or the scalar product of two vectors. And so now the reason why we call it the dot or scalar product, and I'm hoping that this is not going to show in reverse. I don't know if this is going to show reverse orientation. Maybe.
I think so.
Will it?
I'm not entirely familiar with how YouTube works.
I don't know how YouTube works. Is it showing reverse? Saying live here. I'm moving away. Oh no, it's showing the proper format. Okay, perfect. Now it's going to create issues because I'm watching YouTube at the same time, but we're good. All right. So dot product or scalar product. Now, when we're talking about a product, we need to be talking about two things. So let's draw two vectors. I'll go ahead and draw them with a ruler. I will draw one vector in green, and I will draw another vector in red. And so these are my two vectors. And I shall call them something, and just based off of the people that I have in the room, I'm going to call this vector P, and I'm going to call this vector M. And so I have two vectors, and I'm considering what a multiplication of these things might look like. Now there's two ways to multiply vectors, and one of them results in a scalar, and that's the one that we're investigating today. So it would be important to know a little bit about vector P. So vector P has coordinates P1, P2, and P3, or rather components P1, P2, and P3. And vector M has components M1, M2, and M3. Now, you'll notice that they are arranged tail to tail and going out tip to tip. And so this is going to tie back into a question that another student had about when we're measuring vectors and we measure their magnitude, we can also measure something like the angle between these two vectors. And there was some discussion as to whether that angle was always going to be in this particular orientation or whether it was going to be in another method. So I told you you would have to wait for the answer to that, and you're about to see the answer to that as well too. Because an important angle is going to be the angle contained between these two vectors here. And so what is the dot product actually going to investigate with these two things? Well, I'm going to show you first how to compute the dot product. So if I wrote M dot P, what I should result in is I should result in a scalar. Now I'm going to have to turn my screen here slightly. And what it will work out to be is it'll work out to be the sum of the first component of M times the first component of P. So it'll be M1, P1. Now notice no vector hats because we're actually just talking about the magnitudes of these. Plus M2, P2, plus M3, P3. And so adding up all of those products of magnitudes is going to lead me with a scalar value. So if we said that M was the vector 1, 2, 3, and P was the vector 3, 7, negative 2, then this would work out to be 1 times 3 plus 2 times 7 plus 3 times negative 2, and we would just add all these components together after multiplying. And so we would see the dot product between those two vectors as resulting in the scalar 11. Now, seems kind of arbitrary, so why is this M vector times this P vector equal to 11? What does that mean, or what does that indicate? We'll have to go back and tie that back into the geometric representation of the dot product. So I'm going to have to erase a little bit, but this is for those of you who are looking for just computationally, how do I perform the computation? This is an example of how to perform the computation of a vector dotted with another vector in 3 space. Now, in 2 space, it's just as easy. All you have to do is take your components and drop your third set of components. So you'd only be dealing with vector 1 and vector 2's components in the x and y directions, and it would just be that double sum. So we would just, in that case, have 17 if we only had those 2 components from there. Welcome, come on in, it's okay. We are live, so if you say anything, it is going to be broadcast to the world. But it's nothing too fancy. My production value is a little low on these things, so we're not too concerned. And if you do have questions, by the way, in class, feel free to fire out your questions. I won't give names, so I won't name who's the person asking the question, just so that way I don't have to share monetary profits of this video with you afterwards. Okay, so this is an example of what the dot product is algebraically and how to calculate it. But where does it come from? Like, why are we just multiplying these components, and how does that have any connection to measuring anything about these 2 vectors? Well, let's examine measuring them, not with hard real values here, but with another geometric representation. So we've learned how to do some things with vectors already this year. We've learned how to add and subtract vectors. So let's consider a third vector. Let's consider this third vector that connects the tips of M and P. And so this third vector that connects the tips of M and P can be expressed as the sum of 2 other vectors. Obviously, M is pointing in the right direction. The tip and the tip line up. But P is pointing in the wrong direction, so we're going to change its direction by multiplying by a negative. So this is going to be the vector M minus P. And in that way, we've got a third vector now that we can talk about that is related to these other 2. You may notice that I've put M minus P and theta in white, and the reason why I've put them in white is because they connect by some other geometric property as well. If you go back in your head to maybe, I want to say, grade 10 trigonometry, you probably recall being asked questions like this: 15 degrees, and I don't know, maybe this is 11 and maybe this is 13, and they ask you to find x, and you would use a particular property to find x. Now, if this was a right angle here, well, obviously it couldn't be, but if this is a right angle here, we would use just straight trigonometry. But because it's not a right angle, or that's not indicated, we would use another property from trig. Anyone from the comments recognize it? No? Anyone from the class recognize it?
Cosine law.
Yes, thank you for speaking clearly. We would use cosine law to figure out what x is here. So we're going to just go ahead and assume we can use cosine law for this. Now, cosine law for this expression is going to be the magnitude of vector M minus P squared is equal to the magnitude of vector P squared plus the magnitude of vector M squared minus 2 times the magnitude of P times the magnitude of M times the cosine of the angle in between them. And I think I've run a little bit off the screen there. But that's going to be the cosine law for this particular case. Now, neat. There's got to be another way to write the magnitude of M minus P, though. And I think there is. In fact, I think there's a really nice, easy way to write it. Because let's take a look at M minus P here. We've got M as components M1, M2, M3. And P is P1, P2, P3. So we can write M minus P as M1 minus P1. and m2 minus p2, and m3 minus p3. And so that's our vector m minus p yet again. This is just the magnitude squared of m minus p, and this is m minus p. Well, let's actually go ahead and figure out what the magnitude of m minus p is. Now, I'm running out of room right beside, so I'm going to just translate my camera and phone over, and I'm hoping that that's going to give me more room to write. I believe it does. So I'll have to bring the video back at some point to show where we were at. But we're going to take this vector and we're going to calculate its magnitude. So the magnitude of m minus p is going to be equal to the square root of the first component squared plus the second component squared plus the third component squared. Now, fortunately, with this radical here, I can quickly eliminate the radical by squaring both sides. So if I square the left-hand side, I can square the right-hand side, and that will cause my radical to disappear. Well, that's excellent because now I have one expression for m minus p's magnitude squared, and I have another expression for m minus p's magnitude squared. I think any student of grade 10 is going to tell me that I'm going to take one and substitute into the other, which is exactly what I'm going to do now. So I'm going to say that these two underlined portions here are going to end up being equal to one another. So just for the sake of saving some time writing the video, I'm going to bring this down, and I'll probably end up erasing a whole bunch here now. So if you need to pause and go back and write portions of your notes, feel free to pause and go back. This is going to be posted live to the page forever in perpetuity. So I'll just re-erase, and I'm just going to hold on to these two components, setting them equal to one another underneath our diagram. So poor diagram, I've liked it, but it's now time for you to go. And we shall rewrite this as m1 minus p1 squared plus m2 minus p2 squared plus m3 minus p3 squared is equal to, and I really don't like this phone perspective. It's not allowing me to show a whole lot of the board at once. So I'm going to slide back. Now this will be equal to the magnitude of p squared plus the magnitude of m squared minus 2 times the magnitude of p times the magnitude of m times the cosine of the angle between the two vectors. And just checking, yes, we do have enough room for that there. Excellent. Now that we have our two sides set equal to one another, it's simply time to expand. So expanding each of these binomials is nice. It results in a perfect square trinomial. So I'm going to have m1 squared minus 2m1 p1 plus p1 squared. And that process is just going to repeat 3 times. So rather than narrating the entire way through, I'm just going to write the entire thing as quickly as I possibly can and hopefully not make any mistakes. But all I'm really doing here is expanding the right-hand side of this. And I'm happy because these are addition signs in between, so I don't have to get too concerned about any potential sign errors. I just need to be careful that I'm writing the correct indexes as I'm going. So if I'm talking about squaring P3, I need to square P3. Now the left side has turned itself into 3 perfect square trinomials. And those are the results of the expansions of those squares of the independent components of the length of that third vector, m minus p. Now I'll do the magnitudes of p and the magnitude of m. So the magnitude of p is simply p1 squared plus p2 squared. That's the magnitude, but when I square it, it's going to cause the radical to cancel. Oh, I also forgot p3. I forgot we're doing this in 3 space. So this is plus p3 squared, and the whole thing is squared. So that's what the magnitude of P turned out to be. And when we square it, it's going to cause those radicals to cancel. So I will show that whole step, and we'll leave that next step. And I'm going to do the same thing for m, but I think it comes as no shock that it'll be m1 squared plus m2 squared plus m3 squared. And that entire thing will be squared as well because the magnitude of P is squared. But I'm not going to replace the magnitude of P and m inside my original writing of my dot product, so of my cosine law. So at the end, I still have just the magnitude of P and the magnitude of m. Now, as I was talking about, these squares will cancel with those radicals, and I'll have to rewrite the entire thing again. So, geez, just bear with me. Sometimes there is a lot of writing in math, but it's, I guess I should have some music playing, I suppose, at this point to try and make the video a little bit more upbeat. This is where a montage would come in. I think a montage would be an excellent time to show this.
Mandate a carpal tunnel syndrome. Yeah, right on that.
Now, I mean, I am going to have to continue writing here because I have to keep writing these components. Don't forget signs. I mean, I just almost dropped a plus sign there. We have plus m1 squared plus m2 squared plus m3 squared minus 2 magnitude of P, magnitude of m, cosine of theta. And this is exactly why I don't like whiteboards and smartboards, because sometimes you need a lot of space to do something. A chalkboard provides you with that space. Now, it is important to note my equal sign is right here. So I have some terms on one side of my equal sign and some terms on the other side of my equal sign. I'm now just going to simplify this entire expression. Fortunately, I see an m1 squared here and an m1 squared all the way over here. Oh, I don't know if you saw that m1 squared all the way over there, but if you're writing as you're following, you now see that I've canceled out my m1 squared, my other m1 squared. I'm going to have to move this camera back just a touch further and maybe center it so that way you can see all the cancellations. But I think we can predict that most of these terms are going to cancel out. M2 squareds are going to cancel out, M3 squareds are going to cancel out, and the same is also going to be true for all of my P components as well too. So P1 squared is going to cancel out. I forgot the 1 on this one, but that is where the P1 squared term came from. P2 squared is going to cancel out, and P3 squared is also going to cancel out. Phew. Now that I've canceled so many things, it makes good sense to waste more time writing, so continue montage part 2. But all I'm going to have left are the middle terms of the expansions of those perfect square trinomials and the final term of my cosine law. Everything else has canceled. So if you're following along and trying to follow through that, just remember you should have 3 terms on the left-hand side and only 1 term on the right-hand side. Now all 3 of these terms contain something. You should now notice there's a whole bunch of negative 2's sticking around. Now every single term in this entire expression contains a negative 2, so we can divide through by negative 2. And dividing through by negative 2 is going to see all of these negative 2's cancel out as we go. So that will change all the signs of the terms on the left. So they were all negative terms, but we've divided by negative, so they're now all positive terms. So we're simply going to have m1 p1 plus m2 p2 plus m3 p3. That looks an awful lot like the dot product as explained at the very beginning here, where we just multiply the components in order. And that's actually where the dot product comes from. So this is the dot product. Now, it's important to note that the dot product really is just a convenient way of writing a step that is often seen when analyzing the angle that exists between 2 vectors. It's useful in many other applications, but it helps us to represent the cosine of that angle and of the relationship and the magnitudes as well too. Now, it's going to have a lot of properties. It's going to be applicable to distribution over a sum of vectors. It's going to be applicable to factoring out of a scalar multiple. We're going to find that it's not associative that it's not associative because the order in which you do those calculations does matter. But it really seems like it's a contrived set of notation for this intermediary step in a proof. It is. But we just have to be okay with that. Because what it allows us to do is it allows us to have a very quick way of evaluating whether or not angles between vectors are right angles or whether or not vectors themselves are parallel. And so we end up having this expression for the dot product, and I'll have to write it out again now. The right-hand side simplifies by that notation. The left-hand side is the magnitude of P times the magnitude of M times the cosine of the angle between them. So the dot product tells us about the relationship between the magnitudes and the angle between these two vectors. That's how the dot product is derived. And that's how we get to this simple computational method for the dot product. So the dot product relates the magnitudes and the angle, and the computational method comes from the previous step, where we just came up with some notation, much like we came up with logarithms to describe an inverse of an exponential function. Notation was useful, so we didn't have to say something incredibly long. This operation satisfies some notational need for us. And so that is where the dot product comes from. So now we'll just take a look at a bunch of examples of the dot product and how we can run into some neat things in both 2-space and 3-space. So if you're dizzy, I'm sorry I didn't give you a motion warning there. But I will erase the board now. I want to leave it close so we can see. The dot product of two vectors is the product of the first times the product of the second, product of the magnitudes of the first and second times the cosine of the angle between.
But only in 3-space.
No, it's also in 2-space as well too. So this was independent. Like this result would have occurred even if we didn't, and this brilliant question, thank you for asking it. This result would have occurred even if we didn't have a third set of components there, because that would have just simply shed off that third trinomial, and it also would have shed off the third components from each of those sides. So the result actually would hold in 2-space as well too. The result doesn't hold in 1-space because there is no angle between vectors in 1-space, so that doesn't work. Does the result hold in 4-space? Yes. Yeah, it absolutely does. It becomes more difficult to interpret the angle between two vectors in 4-space though. But remember, any two things can be placed onto a plane. So you would now be talking about a plane that exists in 4-space. And it may even be, if you're talking about 4-space, maybe the angle between two planes intersecting in this particular case as well too. Now I just need to be careful there because I know we just went live and I said something and I'm not 100% sure if what I had just said was correct. I will go back and verify that, but I believe in 4-space it will allow you to find the acute angle between those planes had you had them.
Can you find in 4-space the acute angle between two 3-dimensional?
It depends on the basis, and it really 4-space isn't very good for investigating. It's not really good for investigating geometric things. It's more useful for investigating how you can separate structured items into groups. So when we consider 4-space, and we're on a tangent right now, so those of you waiting for the vector stuff, we'll get back to the vector stuff in a moment. But in 4-space, you're really just talking about having 4 distinct identifiable bases for some object you're measuring. Whether that's time, color, size, and a length or something like that, that could be 4-space. And you can have lots of things in that particular space. So when we start talking about objects in 4-space and the way that vectors tend to be used in 4-space, most of the time it's to create separations between subsets or subgroups. So really 3-space within a 4-space is a separation of those 3 things. When we're talking about the physical space that we exist in, that's an easy separation for us to envision because we exist in it. But when we're talking about like 3-space of considering time, charge, spin, and something else, that's not necessarily going to have physical representation, but it can still be segmented off using algebra in much the same way that 3-space can be segmented off from 4-space using algebra. So that's perhaps a really awful answer to a good question. I hope it's in the right direction of what you're looking to find, and I'll certainly look into it a little bit more for you as well too. But good question. Yes, it does apply regardless of the number of spaces you have, because we can simply extend this definition and continue to extend that definition onward and onward and onward. So now I said we were going to do some applications. So we'll go back and just do a few examples of the dot product and where we might see the dot product being used. So example 1, vector I plus 3j minus 2k is perpendicular to vector 2i minus aj plus 7k. Find the value of A. And I love questions like this because it's not just an example that gets you computationally to do the dot product, but it's also a question that gets you to think about the result of the dot product as well too. So I skipped over some of the easier examples. We did do one easier example before, but now we're going to talk about probably the most useful finding of the dot product, which is the ability to classify things as being perpendicular or not perpendicular. So when things are perpendicular, that means that they exist at right angles, right? So these two things would have a right angle. So the angle between these two things would be pi by 2. Now, for a right angle, pi by 2, if I wanted to find the cosine of pi by 2, geez, I would have to consider, I guess the cosine of pi by 2 is 0, is it not? So if the cosine of pi by 2 is 0, and we're looking for something that's perpendicular, that means that the dot product of these two things better be 0 as well too. Because the right-hand side of the dot product, I'm going to use A and B to represent my vectors now, although I really shouldn't because I have A here. I'll use S and T. The right-hand side refers to the product of the magnitudes and the cosine of the angle between them. Well, if they're perpendicular, the angle between them is pi by 2. And if this term is 0, then this term regardless and this term regardless, the entire product here is going to end up equaling 0 as well too. So that's a really useful application of the dot product of vectors. So we know that if I have two vectors that happen to be perpendicular to one another, then their dot product is going to be equal to 0. And so that's the case that I have here. Now, I did give my vectors in standard or basis form, so they're written down with our base vectors. It's probably easier to translate those into column vectors for yourself, so I'm going to translate them into column vectors. So the first one has components 1, 3, and -2. And I don't know if you can see the red very well on the screen. Yeah, you can. It's not bad. I'm going to switch to white though. 1, 3, and -2. And the second set of components are 2, -a, and 7. And this goes from, if you can interpret what a dot product means, from a tough question to a very easy question. Because now we just need to find the value of A when we do that product that leads the whole thing to 0. This is solving a linear equation a la grade 8 or grade 9. So we'll do the dot product between these two things, which I should have indicated with a dot, and I apologize. So 1 times 2 is 2. 3 times -a is -3a. And -2 times 7 is -14. And that's equal to 0. Rearranging and solving, I think we're going to see we add 14, we subtract 2 to get 12, divide by -3. you should be able to get to A is -4. And I think that that's going to be the correct answer. So if A is -4, you would have -3 times -4, 12. 12 and 2 is 14, so that would get us to 0. Now, why is this so important? Well, this is pretty important because if you need to design a right angle in 3 space and you didn't necessarily have a particular perspective, or if you knew that you wanted to fire a booster off the side of a rocket and you knew that that booster is at exactly right angles to something else, you can now determine information about how long the magnitude of that needs to be. You can design vectors so that they're perpendicular if you have 2 things fixed and you want to find the third. The result of the dot product being equal to 0 for perpendicularity is one of the key things that gets tested in IB tests, and it is one of the key things that you see as being an application of the scalar product, because it's really the only interesting cosine. All the rest of the cosines are really not interesting. They're numbers scaling between -1 and +1. And if this is +1, well, then the magnitudes actually matter. And if this is -1, well, then the magnitudes actually matter as well, too. And so the only time we get this unique case where magnitudes don't matter is when we have perpendicularity. So it's definitely the most useful case to examine. And the reason why I start with the first example problem being a perpendicularity question is because it's the most interesting one. All right. Now let's do another one. This is probably a tougher example. Let's do, I don't know, an easy example. Example 2. Find the angle between A, which will let A be 1, 5, and B, which will let B -2, 3. Now, on a calculator-free test or on test questions, these vectors will be designed nicely so that you end up with angles that can be easily represented on your unit circle. So beware, if you didn't like trig without a calculator, it's going to come back to haunt you. You're going to need to know your cosines for our vectors unit. So let's find the angle between these. Well, if I wanted to find an angle between, that's a good indication that I'm looking to measure. And if I'm looking to measure and I'm measuring an angle, then I'm going to use the scalar product or the dot product. So I'm going to just write out the dot product between these 2 vectors. I write out this formula a lot so that way I don't forget it. But the angle between is that theta that we're looking for there. So that is going to be the angle between those 2 vectors. Now, if I'm just looking for the angle between, I should go ahead and isolate it. So I'm going to divide both sides by the magnitude. So I'll have A dot B over magnitude of A times the magnitude of B. And that'll give me the cosine of the angle. And now I just have to go ahead and compute all of these things. Now, I'm not going to show the steps in computing the magnitude of A and the steps in computing the magnitude of B. I assume that you're going to be able to do the squaring and square rooting either on the side or quickly in your head. I will walk through A dot B though. 1 times -2 is -2. 5 times 3 is 15. So that's going to be the numerator. The magnitude of A is 1 squared plus 5 squared, or root 26. And the magnitude of B is 2 squared plus 3 squared, or root 13. And so that's going to be equal to the cosine of the angle between them. Okay, now -2 plus 15 is 13. Oh, look at this. Ladies and gentlemen, I don't know if it's worked out exactly, but I think it may have. The root of 13 times the root of 26. 26 is nicely divisible by 13. So I'm going to write root 26 as root 13 times root 2. Now root 13 times root 13 is 13. So that will cancel with this 13 in the numerator. Canceled, canceled. So now I'm looking for an angle that has a cosine of 1 over root 2. I'm going to go buy a lottery ticket because unless I made a mistake somewhere here, I randomly made up two vectors that happen to be pi by 4 away from one another. So I've run out of room here, but I will continue to extend. So this is, I'm just doing a little twist here. This is 1 over root 2 is equal to the cosine of theta. And that is a special triangle or a special angle that we know. And it works out to be pi by 4. So the angle between these two is pi by 4. And I have no idea how I managed to do that quickly. I'm just going to double check my work. We have negative 2 and positive 15. Yep. We've got 26 when we square and add, and we've got 13 when we square and add. I don't see any problems from here down. So to me, that looks like it's true. If I did make a mistake, I would hope that someone in the class would call me out. I don't think I did make a mistake in any of those calculations, though. I don't see anyone in the chat calling me out. There is only one person viewing, making this officially the second least viewed YouTube live of all time. My paint drying episode, I suppose, got even less views, but only by 100% less views.
Only one student signed in.
Yeah, yeah.
Oh. Was it the whole
I
class
think it's
supposed to
back.
come?
What?
The whole class supposed to come?
I think so. This is going to be posted though, so you can go back and watch if you've missed something, but that's the way that goes. Okay, so that's another excellent example of actually a nice calculator free by chance. I didn't intend for this to be calculator free, I just made up numbers. I claim no, I won the lottery here by picking these numbers randomly. I'm hoping someone will double check to make sure that I didn't make a mistake, because I actually personally find it hard to believe that I was able to randomly pick 4 numbers that yield 2 vectors that are like a perfect pi by 4 separation from each other. But I think it did, so cool. That's it though. So what do we do today? In our lecture, I showed you how to use the dot product, which is the sum of the components multiplied together. And I showed you the key formula for the dot product, which is going to be useful and extended. Sorry. So I did show the development of this formula, and I did show how the intermediate step that led to this point is that named dot product. That's how we take a vector and actually calculate the scalar that is this relationship. This will be manipulated a bunch of different times. And in fact, anytime you see a magnitude, you can imagine that that's probably going to be manipulated with a unit vector at some point, or that's probably going to be manipulated anytime we're looking to project a vector somewhere else. So the dot product is actually going to come up a lot, and it's going to be useful because it gives us the relationship of the angle. This particular rearrangement of the dot product tends to give us a lot of use when we're considering putting a vector onto another vector. Those of you who have not taken physics yet maybe don't understand this, but if you've taken physics and you know that you have a force or a mass that sits on an inclined ramp, very often you have to extend the force to a perpendicular and also in the direction of the ramp as well too. And so when we're talking about a perpendicular force being mapped onto the direction of the ramp, that's exactly a projection of one vector onto another vector, and you would recognize the use of cosine to do that operation already. Vectors is going to give us a little bit of a neater way of doing that projection, or rather just a different notation of doing that projection. And I've now said the word projection a number of times. Those of you who can predict know that projection is where we're going in the not too distant future with this. So that's 2 examples, the development of the scalar product. I'm calling this view done. Thank you to the viewer. Don't forget to press up here so that way you can subscribe for other things. Press down here so that way, I don't know, it does notifications. If you did notice the hotspot over top of the clock the entire time the video has been posted, that's where you click to claim your $1 million prize. Okay, take good care.
No, actually, cosine?
I don't know how to shut off live.
I guess maybe they just haven't checked the